Okay, cool. Hopefully we're online. Just testing out that scene there. Cool, cool, cool. Let's get some tunes. So tonight, it's a big night for a lot of folks south of the border from me, where I live. So I'm wishing you all good luck out there. Peace, hopefully. Although, let's be real. Things are a little bit wild right now. But I hope you're going to stay safe and you're going to be well, and this is going to get... Tomorrow's going to be a better day for you. I really do. Take care about you. Right. So, for those of you who are not out there voting right now in the United States, maybe from a different place, I'm going to do a little Haskell hacking tonight. It's going to be nice and chill. I had to resize everything in OBS because I just changed monitors to a nice bigger 4K display. Messed everything up. But we back. We're good. So I did a little Twitter poll, I want to say a couple weeks ago. Maybe not even that long ago. And we were going to talk about, should we continue doing what we're doing with Rosby, that is writing our own B+ tree, or would you like to move on and just use a library and see if we can make it work? And the vote is really close. Too many people have voted, but this is not a big sample size, but the slight majority is saying that we should try and continue on. After all, we're doing this for learning, for great Haskell hacking, and all that sort of things. Those sorts of things. Oh, pardon me. Hopefully it wasn't in your ear. Okay. So, what are we going to do? I've been doing a little bit of research in the background. Simon, Cypher24, 1024, he was on the stream a while ago. I was working on a proof in 2-3 trees. Originally starting with an idea of using continuation passing style to implement it, and to see that all the properties and variants hold when you use that style and things like that. And it was really complicated. So he says to me one afternoon, he's like, James, I moved away from using CPS and I used zippers instead, and it vastly simplified the proof. You should take a look at this. So I thought, okay. I don't know that I can read the whole proof and understand everything that's going on. But I looked into zippers, and that's what I've been doing this week. Since the last stream. And I thought, well, maybe the way we were going with CPS and the type level programming, we can put that on the back burner. We can see if zippers will get us farther. We might still, by giving up the type level specification of the height of the tree, we might have to test against different trees and stuff like that, write more tests, but we're gonna learn about zippers tonight. I think that's gonna be pretty fun. And then we'll see how far we can get with that. So, thanks for coming by. Let's hack some Haskell. Alright, projects. The old Rosby. Sir. And we'll go to the store and the beach review. Okay. Let's just make sure we got this all saved first. Whatever we're working on here. Ooh. I have some stuff already. Let me get rid of that. Okay. So we're gonna do that again here. Bow, bow, bow. server, source, store. Yeah. Okay, so I'm on this B-tree2 branch. It's branched off of master as its base, which only has this right now. Kind of jumping way back. So we've got node leaves B-tree node like this. A couple things we'll just quickly add here back in that we had before, which was the order as a type. And now there's an interesting idea from Lexi Lambda, Alexis King. She wrote a blog post about how new types don't automatically equal type safety. Bam, bam. Names are not type safety. Oh, we're doing that with order. Kind of true. And there's a lot of good points in here. Alright, we could just make order an alias because it's just an int, really. We're just kind of wrapping and unwrapping it a bunch of times and not really even using new type, like hanging any instances off of it. We just need a smart constructor for it, really. But we could just be careful with it too. So the idea there was that the function order takes an int and gives us an order. X, where x is less than 2, we just give order of 2, otherwise we give the order of x. That's pretty simple. Sorry, that's a new type. Okay. We're gonna get rid of order in here. Oops. Not like that though. Probably like this. And here. And instead of putting those in the nodes, we'll just put the order up here. So one thing I was thinking we could improve leaves here. Get rid of the siblings as well for now. Instead of having, at least at the leaf level, because the invariant is that we can have order number of keys and order number of values that are 1 and 1, we could just replace this with a ordered map that preserves our ordering invariant at the leaf node of all the keys being in their order. And then we don't have to fart and futz around with, when we insert a key, inserting it into the right place in order, and then the value, updating that vector in place. So I think we'll try that out. Maybe something to think about a little later on. As far as the node goes, that's good. We don't really need that. Maybe. Probably. Okay. So how is using a zipper going to help us implement this B+ tree? And what were we struggling with? Or was I struggling with, really? Implementing the other way. Well, we didn't get to the CPS part of, we didn't get very deep into the CPS part of it. But we were definitely struggling with the type part. And that was supposed to pay off, but I was just futzing around with the type variables a little bit too much on the stream. And I also wanted to just see if zippers were a better approach, like Simon was suggesting. So what's a zipper, and how do we go about finding one? Well, the idea behind a zipper is that it allows you to kind of traverse a data structure by leaving a trail. This is the Learn You a Haskell way of explaining zippers, and I think it's pretty intuitive. I think the name is kind of weird, because the idea is that you can zip down and back up the data structure. But have you ever seen like a breadcrumb thing on a web page where you're navigating like, you know, home, and then you navigate to some settings page, right? You've seen those. And you navigate to something else. Ooh. And you can go backwards to the root of the application by clicking one of these prior links and navigating back up. Our zipper is going to implement kind of the same thing for our data structure. So the idea is that we need to create breadcrumbs that would allow us to move up and down our structure. And there's different ways we could traverse it too, like all kinds of different ways. All right, so we're going to need some notion of moving down the tree. And some notion of moving up. Now, what does down mean? Like, what do we need? What does it involve, right? Well, say we're starting at this node here. And, like, let me just change the color here. We're starting here, right? We could go down to any one of our children. If this was, say, an order 4 tree, there could be up to 4 children here and 3 keys. So we'd have to give an index for which branch we're going to take. Right, so if we're going to say go down this one, all right, that might be index 1. This would be 0, 2, 3. So we'd need that in order to do down. And we operate, this down operates on zippers. So that basically means we need to have an integer index as an argument to down, as well as a zipper. And that's going to return us a zipper. Right, and what's the zipper going to be? Well, it's just going to be the node we're currently at, the yellow dot, say, B tree node, the B tree. That's going to be KV, and the breadcrumbs. That's basically the stack of movements that got us to where we are in the tree. Now, when we think about down, that's pretty straightforward. Right, we just need the zipper. The zipper's going to have a KV as well. Now, when we go back up, it's going to be kind of the similar. We're going to need to be able to reconstruct the parent node. So if we're at a leaf, there's 2 kinds of node. There's leaves, and then there's internal nodes. But no matter which one we move up from, we're going to get to a node. Right, if leaves are always at the bottom. There's nothing below them. So that moving up from there only means that we can only go up to an internal node. And if we're at an internal node already, and there is something above us, we can only move up to another internal node. We can't move up to a leaf. Right? So we don't need a parameter there to go back up. We just need to give the zipper the current state of whatever zipper we have when we get back the next zipper. KV. And that's about all we need. Just to go down and up at least. And probably to move around our tree. There might be other operations we could do with zippers to do stuff, to search, things like that. But that's the general gist of that right there. What else are we missing? So this is the zipper KV. Crumbs, right. So in order to get back up to construct the node above, that means we need in our crumb the state of the parent node so we can reconstruct it and move back up the zipper. Because this value here is only the currently focused node wherever that dot ends up. So if we go down, we're moving this dot down to here, and so this node will become, in the zipper we return, the B-tree value there. And then the crumb we're going to add should contain enough information that if we want to move back up again, we can reconstruct that parent node. So crumb then, down crumb is basically going to be that. It's going to have the int. It's going to have everything we need to reconstruct a node here. So it's going to have an order, vector of keys, and the vector of nodes. And this should be that. That's the crumbs. Hope you're with me so far. Let me know in the chat if if you have any questions. I'm happy to answer them. Okay. So let's go implement some of this. I'll leave it up. Okay. So let's define the crumb. That's going to be basically down, call it. And that's going to have an order, a vector of k's, and a vector of B-tree. I might need to derive some basic instances, maybe. B-tree node. Oh, I don't call it B-tree node. Let's just call it B-tree. Yeah, okay. Good, okay. Like it? Love it? Maybe? Okay. So then, our zipper KV is just type it as a tuple. And the list of crumbs. I can type properly. That would be nice. The list makes a good general purpose GP stack. Cons on the front of it, and take the head off and kind of things, so that's good. And this is going to be a pretty sparse tree as well, so I'm not too worried about that becoming too big as we traverse this thing. The other thing that Simon was mentioning about this approach that he was kind of concerned about with his implementation on Proof was just if we could avoid stack allocations from the CPS style. So not really sure if that would be a huge issue. I'd have to play around with the two approaches, I guess, if I end up writing a second implementation to compare them. I don't know how that would play out in my head anyway. But this looks pretty good. So we got the zipper, we got the crumb. What else do we need to implement? We need to move up and down. Up, down. A zipper KB. And a zipper KB. And the other thing I was thinking about this too is that there might be some properties to here as well that we could check. Right. Because the notion, the idea of moving down, if there is something to move down to, and then we move back up, should originally get the root of the, say it's from the root. I'm sure we should get back the root again. There's something else though that we're missing here, and that's just that the return of these zippers, like moving down, because if we try to move down operation from a leaf, what do we get? We can't move down further than a leaf, so we need to embed a notion of nothing being there. Same with moving up. Once we get to the root, we can't move any further up. So we're going to need maybe there as well. Okay. I'm going to take a drink. This is my green juice, healthy juice. All right. Hydration's important. Okay, so moving down now. Let's work on that one. We have the index we want to move down to. And then we can basically pull apart the zipper. We're going to need the B-tree node in case of nodes. Well, let's just do the leaf first. We actually have a leaf. It doesn't really matter what index we give it. Forget the order, forget the leaf itself. Forget the breadcrumb trail. It's just nothing. However, if otherwise we have an index, we have a B node that we can move down from some order. I think we just need the order. Then we have to pull apart we could pull apart the node itself to get the keys and the chillage files and the crumbs. Okay, let's get rid of our drawing here. Alright, so here's our hole. We got to return a maybe of a zipper KV. Pretty straightforward. We have the list of crumbs in scope. Our goal right now is going to be just to add a new crumb and focus the next node to be that child that we selected by the index. So that means we need to get that child out of childs. And I might use the do syntax here maybe. Because if we try to get any index out of childs, of course, there's a possibility for that to fail. So we're going to need to import vector. We should probably clean that up. Qualified. B, and we'll also pull in a handy dandy what? Operator. Child's what at the index? We'll get C, and if there is no such child there, then that will return nothing as well. Can't move down there. Sorry. But then, all we need to do here is actually, this might just be able to fmap over this results. Because all we're going to do is put C here, and then we're going to create down. What are we going to do? We got to get order, phase, and childs. And we got to cons it onto C's. Yeah, so that is totally f-mappable, I think. We can get rid of pure. We can only make this a function. Yeah. Tuple section. Yes, thank you. That's exactly what I was thinking. We might need that. That would be. And then we can get rid of the C here. Redundant. Butte. Cool. So let's move down. Let's just write out a few examples for us to play around with in the REPL. So we just have a B tree of like things car, maybe? Not car, no, char. Example 1. So, example 1. Let's make it an interesting one. Be node, say of order 4, and let's give it some keys. I don't know, say 2 and 6. 2 and 4. Of course, we can get these. Right? Hey! How's it going, Beavish? Beavish? Ben? Ben's alright? Yeah. Last few weeks have been going okay. I've been mostly working on the text adventure stuff. I've been off work. I'm just kind of having fun with it, but I've kind of kicked back into Rosby a little bit. I'm trying out yet another approach to implementing this B+ tree tonight. Right, Ben. Good. So nice to see you, Ben. Thanks for popping by. Yeah, so we're working on implementing a zipper for our B tree structure to help us actually generate it and implement insert. Zippers would let us kind of move around the tree just using these operations on zippers, moving up, moving down. And I'm hoping we'll be able to write insert in terms of them. Simon mentioned that he wrote a proof, and he wrote a proof that zippers implement the same properties as doing it in a CPS style, but it made things a lot simpler to prove, so maybe it'll make our implementation a lot simpler too. Just learning. So we got to give a couple of nodes to leaf nodes to go down to here. In our example, a leaf in the same order. Yeah. Give that. Be the leftmost one, so it'll be like 1, 2. Well, it's going to be a vector, of course. And then that's going to be, say, A and B. Oh, got parser or something. Yeah, oops. Oh, I did need that square bracket. Ah. Okay. Let's check it out. Node. There's keys. And children. So maybe let's make that 3. I don't know. This isn't exactly a well-formed tree. Just an example tree, just to demonstrate the movement. I have that proof on hand. Simon did some mealing to it, but I don't have it with here. But if he happens to pop in the stream, we'll ask him about it and we'll look into it. Maybe he'll be brave enough to join me on a stream once and he can walk me through it. Walk us all through it. Alright, so if we have example 1, if we move down to 0, we should get that to that leaf node. But we need a way to wrap up our node. Example 1. Return, example 1. I can move down 1 or to 0. But I got a type error, so I can't. Oh, yeah, of course. There. Yeah, I can't, I'm not, yeah, I gotta put this in a zipper, not a, yeah, example 1 should be there, and the zipper, the starting zipper should be the empty list. There we go. All right, so by moving down to 0, the 0 branch, here we have just this zipper here, where the leaf is now the currently focused node of the tree. And then we have this list with our breadcrumb in it down order 4 with the 3, 4 keys, and the list of the children of the parent, of which we're also a member here, the ones currently focused. But it means that we can implement up now, and we can implement move up. So let's go ahead and do that. We just have the zipper that we need to pull apart, right? So we can, if we have a leaf node, I don't think it actually matters which node we're focusing on when we're moving up. We just need to, we have the empty list. That means we're at the root. So we just return nothing. Otherwise, we'll have a crown, we'll have a down on it, on the list, which will have our order, keys, the child's, and potentially some more crumbs. So in order to move up then, we need to return our zipper, of course, but we're going to construct, reconstruct our B node of the order, and we do with K's and child's. And then whatever's left in the crumb trail can go there. Of course, we have to return that maybe, so just, it's pretty much as simple as that, I think. So we move down to 0 and we move back up. we should get the root node again. All right, we get order 4. It's a node type. Yep. Keys 3, 4, which we had before. And then our list of children. All right, we can keep doing that. We can move down to 0 again. And back up again. It's the same thing. Right? We try moving up twice. We should get nothing, of course, once we're at the root, because we'll be at the root node. And if we try to move down more than once, even if we try to move down at a leaf, we get nothing. And if we try to move down to an index that doesn't exist, a child that doesn't exist, we get nothing. That's about as expected. Now, often when you see zippers, at least in, say, Learn You Haskell or something like that, they implement in terms of binary trees, and they have like different types of moving left, moving right. They don't give a specific one, but I feel like this one needs to have an index. Just because we're an M-ary tree, and so there could be M number of children that we could select. And moving, the idea of moving laterally, left and right, we could implement that with zippers, I think, because the only case we'd have to handle is the leaves, of course, and they would have, if we were to implement this as like a traditional B+ tree with those links, the linked list of leaf siblings, we could do that, hopefully. We'd probably still need I/O to make it efficient, perhaps, but it's there. One kind of warning, though, when I was looking into learning zippers and stuff about that this week, the first package that comes up on Stackage when you search for zippers on Hackage, sorry. This one kind of got me a bit. Like, okay, I just learned zippers from Learn You Haskell. Great, cool, I get it, totally understand. It's great, straightforward. You're like, okay, well, maybe there's a library. This is probably a pretty common thing. I've heard of these zippers before. Okay, zippers. That's a top search result. It's probably exactly what I'm looking for. It's a commit library, which is great. Don't get me wrong. But it's very, 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 very general, of course, because it's using lenses and traversals and optics and stuff. And for the life of me, I couldn't get it to work with this data structure. And I even asked help from the great Chris Penner, who wrote Optics by Example. And I think we came to the conclusion that just writing a concrete zipper for a data structure like this works pretty well. So that's what I'm doing. Pardon me. Yeah, so we got move up, move down. Well, that's pretty nice. Let's just, I don't know, add one more leaf just because we can. Okay, order 4, and let's just say this one is 4 and 5. And we'll make it C and D. So let's move down to 1. Cool. So that's CD. Move down to 1. We can move back up and then move down to 0. Okay, at AB, that's what we're currently focusing on. And then if we go back up to the root again, we're at the root. How cool is that? How cool is that? It's pretty cool. All right. So check. We have a zipper. We can now zip up and down our tree. What else do we need? We need to be able to write insert. That's what we're really working on here, right? The cool thing about zippers too, yeah. Oh, I don't want to run on a tangent here. Yeah, we need to be able to write insert. So now we can go traverse up and down the tree. Need to be able to write insert. So what does insert look like in this zipper universe, at least? Well, I think it's going to have the same top-level signature as before. Our users of our libraries don't really need to know that how we're traversing the tree or how we're representing it internally, just like when we're trying to things out with gadgets and that sort of stuff. We kind of want to hide those implementation details, so I think the type signature is still going to look the same. We get a btree kv back, right? What's our term going to look like? Well, we're going to have to pull the key. We're trying to insert the value and say we have to zipper it up. And then we got to give it to some other function. Okay, we don't have zipper defined, so let's just go define that quickly. That's just going to take a btree. Let's make it very, very specific. Right. Super simple. Very, very concrete. No polymorphism here yet. It's okay. Alright, so we got to combine that with a function. What does that function have to do? Well, let's look at our hole. Right, it's got to take a zipper kv to go back to a btree key value. Right. We still haven't really done anything with inserting. So I'm going to insert into the zipper. Insert prime, insert zip insert. Insert with. Okay. What's insert with all about? Well, it's going to take word k, key value, of course. And it's going to take a zipper of key v, or zipped up btree. Get back a zipper. Okay, I'm not going to implement it yet. I'm just going to leave it undefined. I want to finish this formula first. Well, then we got to get the finished btree of insert with out of the zipper. And we don't want to just get the currently focused one out. We want to get back to the root, get the root of the zipper, and return that node. So we're going to need a move to top function. That takes a zipper. And then we can unzipper, wrap it back out again. So we have move down, move up. We'll have to implement move to top. That just goes zipper to zipper. And on zipper. Just returns the T. That one's pretty easy to implement. Okie dokie. So let's go fill in these holes. These undefined holes. What do we have undefined still? Insert with and move to top. Move to top is going to be pretty simple, so let's do that one just quick. I think. We can destructure out the zipper. We don't really care about the currently focused thing. If we have... Well, we only care about the currently focused thing, actually, if we're at the root. That's just T. Or, no. There you go. Oh, that should be fine. We run out. That's all we care about. Is the root. That seems kind of like a weird formula. Otherwise. Or a weird equation. But otherwise we have a down. Just like we have before. C and C's. And while we have those childs, we're just going to move to top. Oh, wait, we just have a Z. I'm just going to keep moving up. No, that doesn't make sense. That's infinite. No. Let me think about this again. Zugga. The notion of moving to top is just, we just keep calling move up. Until we have nothing more. So... let's do that. Let's case move up the zipper. We have nothing. And we're at the root. Right, and we can just return C. Otherwise, we have another zipper and we got to keep moving up. Next one. Or move to top. Right. Okay. I think that makes sense, right? So try and move up from the zipper that you've given us. If there isn't, that means we're at the root. Okay. And if there is, we move to the top from that. From that one. Okay. So we still have some undefinedness. Some unfinished business. Insert with. Okay, so what does insert with now do? This is where we do the real work. Now we're in zipper land. Okay. Let's think about leaves. open there. Pull apart our zipper. So at the bottom we'd have the leaf. Some order. Node with some keys. This is where we might want to do the ordered map thing. And we have some more crumbs. I don't know if we're going to use the crumbs. Right, okay. So let me not delve into the silence of my own thoughts here. Let's discuss what happens when we get insert with, or the currently focused node of our zipper is a leaf. Presumably, in the case of insert with, the idea is that we get to, when we're searching a B+ tree, let's start with that. We got to find our insertion point. So we're going to eventually traverse to a leaf node at some point. And I don't know, we have 2, 5, 6. We want to insert 4. And we're going to make 4 a car Z. I don't know. All right. So we got to find our insertion point. This might be just 1, 2. This child here could be, or no, this would be, sorry. So this might be like, say, 0 and 1. 0 might have A, doesn't really matter. This one would have 2, 3. This child would have, so let's make that 16. This one could have 5, 7, 8, 10, and this one would just have, say, 16 and 17. Oh. Right, we want to insert 4. So we got to search through here in order to know where to insert it, right? So we're going to do some kind of search inside this node and find out that, okay, 4 is greater than 2, but less than 5, so we got to go down this. We're going to call move down on the zipper. So when we talk about internal nodes and we do that branch, we got to remember this part here. We're going to move down on there. We're going to hit a leaf node at some point, which is the case we're working on right now. And inside that leaf node, we have, I think, to handle 2 cases. The ones we know pretty well by now. We have to handle where we can just insert it and not violate our invariant on the number of keys we're allowed to have. Or we cause an overflow because we violate the invariant, and then we have to resolve things. Yeah. That's basically what we got. So I think the easy one, none of this is super easy, but I think the easy one here is to just keep the leaf node as is because we have room to insert. We need to kind of know about that part. So how do we know that? Well, the length of K's, this my vita length of K's, less than, this is probably where our new type wrapper kind of gets a little annoying. I can't just give it generalized new type derived num. So it still wants to convert it to an integer with less than when this is an integer on one side. I don't know how to resolve that. But anyways, that's neither here nor there. Otherwise, we have the other case where we have to like do the splitting stuff. Okay. What are we gonna do for this one? This is kind of where I want an ordered map. Because I don't want to have to like manage two vectors, add all this extra stuff to figure out what index to insert the key at, and then, yeah. Let's see if we can find one. Stoppage. Ordered containers? Is that a thing? Yeah. Okay. Oh, it only remembers the element, the order the elements were inserted in. That's not going to be quite what we want. Is regular map ordered in terms of a key? I wonder. Yeah, that's not what we want. Maybe regular map is just fine. Otherwise, we might just have to stick with double vectors. But okay. It's slow. Containers. Yeah, I don't need all that. Okay, well, it's not too different on package anyway. Containers. There's different types of containers. Right. Data.map. So it inputted ordered maps from keys to values. Ordered. Does that mean what I think it means? I think maybe it does. Yeah, okay, I think it does, yeah. Okay, so regular good old map would be an ordered map, the kind of ordered that I want. Cool, 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 cool. I think that would be okay. If we use that, then yeah, I don't have to worry about the looking at between the two, like keeping the two vectors in sync, I believe. And it also means that we should still have our same search guarantee. O log of n, yeah. Yeah, so we shouldn't. We'll still be within O log of n for when we're doing searches on this thing if we use a map. So that's good. I like that. Let's try it out and go with that. Just want to make sure that I've got that. Continues. I don't. I'm going to do that as well. Give it a map.script. Map. Qualified. Map.script. That is n. Okay. And that means leafs, keys, and values could just be values. That could just be a map. KB. And this nonsense. Becomes a little bit different. These. Then length, it's not vector length anymore. We need the number of keys in y'all. Size. Potential type errors here, and our, yeah. What that was. 1, 2 to AB, okay. We want that as well. So like say for C and 5. Okay, back to where we were. No problem. We only can't really do that at a node because, of course, the number of keys we can have in a node is less than the number of values we can have, so they are technically separate. So we do the node stuff. That's going to be there. At least we can avoid it on the leaf, on the leaves. Okay, so yeah, where this becomes pretty straightforward then. We have to return a zipper here. Bleaf with the same order. Yeah, that is kind of gross. and a leaf with, is it insert? K and B. And then C's is unchanged. Oh, wait, I gotta give them that as well. Okay. Cool. Thank you for the suggestion. We can make that a new type now. Great. Otherwise, we're full. All right, this is where we need to split. We do that split operation again, where we split our map in half. We create, and then we got to do something about creating either like a new parent node and putting those as children, and then merging that node at a level higher. If we could do that in terms of zipping around our tree. That would be pretty boss. But what would happen? What would that even mean, right? So we have a case where, no, let me do it. Say we're at an order 3 type thing, right? And wherever we find ourselves at the bottom here, trying to insert value into this node here. And when we do that, we cause an overflow, right? Because we would hit this branch here, because the size of our map is going to be too big to insert into. In that case, we needed to really split that node into and probably be, depending on where we insert it, maybe like 2 over here and 1 over here. And the one we're trying, the middle one, whatever the middle one happens to be, would become a parent node. So this will become an internal node. And these guys, these ones down here, will be new leaves we just construct. Then we need, and the current state of our zipper, by the way, is that we're still focused on this node here in this branch. So we construct this in this branch here, then what we need to do in the algorithm is try to merge this one with the parent of the currently focused node. Right, so I'll draw the little, the yellow dot here. So we're focused on this node, the current state of the zipper. All right, we construct this on the side. Then we got to do this kind of merge thing with the parent node. Right? So really what I think we need to do there is we split it, we walk up, or we move up. And try to merge this new node in with that. So we might need a composition of and moving up. Oh, that's gross. Move up after merge? No. Merge after move up. Yeah, that makes more sense. So move up takes a zipper. It gives back a zipper. So we give the current state zipper that we have. We call move up to get the next zipper. And we give that to this merge operation. What is this merge operation? This merge operation also needs to know about the node we just constructed as well, won't it? So merge then is going to have to take the newly constructed B tree node that we want to merge with. The zipper. So it's going to have to do it inside the zipper and then returns zipper. So this thing here, this function, that looks like we should give that a name like merge up. Because once we get the zipper back after we merge, we might have to do it again. If we cause an overflow in this situation. All right. So let's say we have fairly sparse tree, whatever. It's like all the way down here. Right? I'm gonna do move up, merge up. And then this causes an overflow in this node, so we also got to merge up again. And then hopefully what we end up with would be three nodes and a bunch of children down there. That seems reachable and doable. So. Up. Let's do the insert with. Okay, so we're in the overflow situation. In the overflow situation, we are going to what do we need to do? We need to pull together our list of keys. All right, yeah. List our keys. And I think that's the operation. We list the keys, we take the midpoint, and make that middle key the parent. Everything that's less than that key becomes the child, and that key and everything greater than it becomes the right leaf. And then we do merge up. Yeah. So let's see. Basically, we could do that by inserting into the map. Is there a way for us to split a map in two. Union with, unions, difference, intersection, disjoint. Oh no. Key, sorry, not merging, not mapping. Folding. Partition, maybe filter. See, also split two. Oh, yes. It. Oh, I think this is it, friends. Split 4. Oh, we kind of want it like split in half though. Not split by key. Oh, no, actually, like, that could be fine. Right, we could just calculate the midpoint and split and call this operation. Because that's also going to be the key in the node. Parent B node, the internal node. Yeah. So this should be good. That's great. Map.split. I like it. Okay. So let's get that. Insert into our leaf with these. Okay, so V's prime is like our overflowed. Overflowed map. It's too big. We gotta preserve the invariance. Okay. For the midpoint, then becomes low, which is going to be 0, plus the n.size of these. Oh, it's just going to be n.size of these. We don't have to do that. I'm thinking of binary search for some reason. .5 of these. Division 2. Okay, and P prime will become the value that's at mid. Of course, it's probably going to return a maybe, because looking up in a map will do that to you. Even though we know it has to exist. Because you can't construct a leaf less than order 2. Except for the root, so maybe it's not such a crazy thing. So let's see how we're going to do this. Not insertion. Look up. Yeah, we're going to get a maybe, of course. Okay. Okay, it's okay. It's okay. What are we gonna do? What are we gonna do? What can you do, really? Nothing, I don't know, really. But in the case where we do have that value, now we can cook. Getting a little bit nesty. How's that doing? K prime, we're gonna find the lower map and the upper map. And the left leaf. The left and the right. Colloquially. And let's split. Mid. Then we need to construct that node and merge up. And we have to merge up the current zipper. The B tree, the node, order, node. Well, it's going to have v dot singleton, 9, and our children are going to be from list of left, right. And the zipper. I think that makes some amount of sense. Something not too merge up again. Let's merge. So it's going to take a B tree of KV. Gotta return a zipper of KV. It's basically going to be. Oh, yeah, I probably want to flip the arguments around. So that's going to be a zipper. Second argument. Yeah, so it's about okay. Yeah, and then merge. It's almost exactly the same, isn't it? What's merge got to do? It's got to take that B tree. It's got to take the tree, the node it has in the current state of the zipper, merge the node it was given with it. And if we have an overflow state again, we have to call merge up. Or we have to construct the node again and call merge up with that. And doing the splitting again and all that sort of stuff. Nah. And then just call merge up again. But otherwise, we just merge that node and then we stop. And insert with, we'll return that. Move to the top of the zipper, so if we only zip up to 2 levels and there's a third, it'll just go all the way to the root and remove, and then we should have our B tree. I think we're making some good progress here. I'm gonna have to thank Simon later. Unless you're watching, Simon, then thank you. So well, we might have a bit of a, we might have got a little zealous here. We might have to think things through a little bit here with merge, because of course we could pass a leaf here, which we're only really interested in B nodes, not B leaves. When we're doing merging. So this could fail if you give me something I can't do anything with. That does mean we have to do a maybe zipper. We could just say, like, if you give me junk, just gonna return the zipper I got. I can't merge anything. I can't merge leaves. I don't really know if we care too much. It's kind of an internal function. I'll just kind of document that. So we merge a B node with the currently focused node of the zipper. We ignore B leaf. And return zipper. Changed. Which is kind of applied to the needle and stuff, yeah. Yeah, I think that makes sense. We get a B leaf. Doesn't matter what order and leaf it is. Whatever zipper we get, we're just going to turn on zipper. Otherwise, we have a B node. And it's some keys and some clouds. And we do have to tear apart the zipper. We need to get the B node out of it. Oh, well, that means we got another case there as well. O prime, case prime. I think. Okay. We have another case to handle, of course, if currently focus node is a leaf somehow. which case, if we have doesn't really matter what this is. And if the head of our, the currently focused things of B leaf, whatever something, whatever files, doesn't really matter. We just want to kind of turn that off as well. Okay, this is the only real case we care about. Tick-a-tick-ow. Mm-hmm. Oops. Okay, cool. All right, what else do we need? So we've got childs. So yeah, this is where things are going to get a little bit hairy because splitting internal nodes is a little bit trickier. Okay. Actually, yeah, it just occurred to me that maybe we could still do some height tracking here to prevent degenerate trees, but maybe another time. Okay, so basically we know that we can safely merge this node because its k's length should be a singleton vector, so it should only be one. And when we do the merge operation, and we know the size of k's prime, and we know the order of the node. So if by inserting it we wouldn't violate the order constraint on keys for internal nodes, then we could just safely do an insert like we did with however we merge them internally. So we still have to maintain the order invariant, and then then we can handle the other case separately. So let's kind of guard that, I guess. So I say the k is prime, the length of k is prime. It's less than. So if I got order 4 on an internal node, that means I can only have 3 keys. 4 children. So O prime O minus 1. Doesn't matter, we'll just deconstruct this one. Something like that. I'm a little bit off the home row here. Otherwise, something else. Cool. Okay, so what do we do? We've got to figure out how to merge these two things together. So on my left, I've got vector of k's, vector of these, and as my input, I've also got actually, it kind of looks more like this, yeah. Yeah, no, this will be fine. Some number of children. And then I've got this one with 2. What I want to do is insert this k into this vector of k's in the appropriate place so that the ordering is maintained. And these children of this k also need to be put in the appropriate place. All right. Now this means that since this is a vector, these are going to have indices. Actually, probably just draw it here, like 0, 1, 2, right? This is also a vector underneath here, technically. All right, let's go 0, 1, 2, 3. So this is an order 4 tree. That means we do have room for one more. Or, sorry, order 5 tree. It means we do have room for one more to insert this. So we should go to this branch here. And this is gonna be a little bit tricky. A little bit. So I need some function that will, I guess, take a vector and a vector, or a vector and a singleton vector, or a vector and a value to insert into that vector, and give me back an index of where it was inserted along with the vector. I need to know that, because depending where I insert it, say, I don't know, it's 1 or whatever, I got to make sure that these 2 children then get inserted into the appropriate place on either side of that, I think is how it goes. Right, so that would overflow, that would break the invariant on the number of children, though, if we had to insert 2 into here into an order 5, because we already have 4. That would make the number of children 6. So I wonder if this is actually 2. Order minus 2. Let's double check that just to make sure. they have to have at least b minus 2. Let's be branch rate factor order. Okay. Max number of children is b. Min number of children. Keys. I guess it only cares about the children then. I don't see anything about that. Keys. Oh wait. Minimum number of keys, maximum number of keys. That's throughout the whole the order tree. Oh yeah, okay, I guess it only cares about the number of children. Okay. We're looking at the wrong thing there. We're doing our guard. So it's good to double check that, yeah. We got it pretty much on the nose there for leaves. And then the root node has this special invariant at most b minus 1 keys. I wonder how we're going to track that. Okay, so it doesn't matter about the length of the keys so much, it's the length of the children. Child's prime is less than, and it was yeah. Less than or equal to O. Then we can do the merge. Yeah, so we still need to figure out the index we inserted the key into, and the newly created indexes in order to construct our newly merged tree node, so that we can put those childs in. Oh, we need to make sure we have space to insert them. That's right, so it's not less than or equal to O. Less than or equal to O minus 2. Okay, so the order's 5. We have only 3 childs in the existing node we're looking at. Then we can insert 2 more. Still be good. We can merge. Otherwise we can't. But, we are running out of time, friends. Goodness gracious. We only got 5 minutes left. Oof. So, we are basically going to need to define. I'm just going to make a local let binding for this keys prime time. AI. Insert key. That would be the keys. This one here, which we know is only going to be a single element here, but Haskell's not going to believe us. so this might get a little bit of. What I want to be able to write is like case prime, or I'd really like to be able to just tell Haskell what that's going to be. But I can't, so anyways, I want to be able to do that. Hopefully it's not too bad. And I want to insert that value into case. No, case prime is what we're looking at. Case is the one that we had from case prime, so that's going to give us the index that we inserted at and the completed merged list of keys. Then we need to have a function for generating a new child. Child's prime time. It's our child. And that's going to be at an index, ki. It's going to be our input childs, which will be the one left over here. Childs into child's prime. And we're going to have to totally clean this up later. I'm not sure if I'm going to remember all of this next week. We'll see. We'll see. Okay. And assuming we have those things and they work, then what we should be able to do is return a new zipper of our merged data. So it'll be a B node of the same order. Use order prime since we didn't unwrap that one. Of a node with K's P prime prime and child's prime prime. And the rest of the breadcrumbs still intact. We got his input. So we'll actually need those. What's this going on here? Oh, I uncommented the wrong one. This one over here. That's the one that's going. Yes. So I'm just going to make a dummy type here. So I can copy the type and insert child's. Can I wonder if this would be a better way of doing that. Enabled, yeah, partial type signature still, so I don't know. It'd be nice if we could just, if there's a way I can get GHC to write that out for me, that would be nice. And this foo trick is okay for now. Clean that up. Right, so insert childs, that's T0 is going to be what? That's our index. t, its return type has to be a vector b-trees. That's what we need to do there. Right, and once we can define those two things, and that path of merge will be done, and we have to handle the otherwise case. What's the otherwise case here? That's the overflow case where we need to figure out what to do there. So we'll do that next time, because we're kind of out of time. So yeah. There we go. This is, zippers are all right. We haven't really, I feel like we could write more properties for them. And we'll write some tests for our data structure using this approach, but this is looking pretty good. Hopefully the code isn't too hard to follow either. So I'm gonna roll with this. Me likey. Okay, let's create a commit. What we've got so far, at least. It's not finished, it's work in progress. That's okay. But we'll fix it up before we push it up, I guess. Yeah, so if you have any questions, feel free to interrupt in chat. Yeah, I think so too. I'm feeling a little bit better about this. I mean, we didn't get too far into the CPS approach because we're getting distracted by the type level stuff. Yeah, this is turning out to be, I think, a little bit easier to follow. For sure. So maybe this is the way. Yeah, so this is going to be a work in progress. So we're going to have to get a zipper, concrete zipper. When I say concrete zipper, because I'm literally writing out the zipper just for this data structure very concretely. Instead of generically, where I might add a little more polymorphism so I can create zippers for other data structures. Which you can do with the zippers library, but sometimes if I don't know, the reason why I got from I understand from Chris was that zippers, the library wants to keep track of everything at the type level, and if you're trying to stack together a bunch of things that change types in that stack of traversals, it's pretty wild and pretty hairy. So sometimes just writing concrete zipper, it's not too hard of a concept, I think, to get. It's pretty all right. Navigating B-trees. And started implementing insert terms of them. Terms of, okay. Yeah, so we added a concrete zipper for navigating the B-trees, and we started implementing insert terms of it. That's good. So we'll see you next week. This is my last week as a unemployed individual. So Tuesday, you might see me just Tuesday, or I might try and do as many streams as I can before Tuesday. We'll see how it goes. But may all your monads be free. May your types always check. And have fun. Hack some Haskell once in a while. And tell me about it. You can follow me on Twitter at AgentUltra. You can find my YouTube videos probably from there. Or we mentioned the functional programming Slack. You can look that one up. There's a Zulip as well. And yeah, talk to you soon. Peace.